In this series of videos, we're going to talk about suffix indexes. So these are indexes that work fundamentally by taking all the suffixes of a text and organizing them in some way. We've already seen a data structure that can function as an index. I'll put in the video description a link to another video where we discussed this kind of data structure. Specifically, we talked about a Kamer index where we might have a text and we extract all the substrings of a certain length from that text. In this picture, we've abstracted all the substrings of length 5, so all the 5mers, and we put them all into an associative data structure of some kind, where associated with each substring is the list of offsets where that substring occurs in the text. Okay, so we've already seen this, but we're working toward a different idea of a index that organizes not all the substrings of some length, but all the suffixes of a text. Okay, so this is a different approach to what we've seen before. We want to organize all the suffixes of the text T, and surprisingly, to a surprising degree, we can make pretty economical, efficient, practical data structures out of these collections of all the suffixes of a string. This series of videos is going to focus first on tries and suffix tries, and then we're going to build upon suffix tries to get to suffix trees, and then that will also be a nice jumping off point for suffix arrays. There is a separate playlist, and again I'll put a link in the video description, where I talk at length about another related kind of index data structure called the FM index. That's not the focus of this series of videos. This series of videos is really focused on getting through suffix trees and suffix arrays. Okay, and we'll start with the basic tree-shaped associative data structure that these are built on, which is the trie. Okay, so what is a trie? Well, first of all, a little bit about the word. The word trie is spelled T-R-I-E, which is a little unfortunate because that looks like it ought to be pronounced tree. And a trie is a kind of tree, but it is not the same thing as what we mean as the general term tree. But, okay, so it's spelled T-R-I-E and it's pronounced trie. To add another bit of confusion to this issue, it comes from the word retrieval, right? So it's the T-R-I-E from the middle of the word retrieval, and so it seems like it ought to be pronounced tree, but it's not. It's pronounced trie. And a trie is a tree that represents a collection of strings. And the strings that we're putting into this data structure, we're going to refer to these as the keys, right? Because we're going to put the strings into the data structure, and then later it's going to be possible to query the data structure to figure out whether the string is in there or not. I'll give you the longer form definition of what a trie is first, then I'll give you a shorter explanation. But in the long form, we say that a trie is the smallest tree such that, first of all, each edge in the tree is labeled with a character C from our alphabet, sigma. Right, so sigma is the alphabet. If we're dealing with DNA, then sigma is just the set containing A, C, G, and T. If we're dealing with English language, then sigma is a bigger set. But each edge is labeled with a single character, exactly one, from this set sigma. For a given node, at most one child edge, right, so there's going to be parent-child, this is a tree, so there are going to be parent-child relationships. And for a given node, at most one of its children can be attached using an edge labeled with a particular character C. So in other words, there can't be more than one child labeled with the same character C. We're connected by an edge labeled with the same character C. And each key, right, our keys are all strings. So each of these strings in our set of keys is spelled out along some path starting at the root, which is to say if you were to start at the root and walk down, boom, 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 and follow edges on the way down and read off the characters that are labeling those edges, you'll be reading off one of the keys. Okay, so that's the sort of long version. And you can see it's important to emphasize we're talking about the smallest tree such that all these things are true. Right, the smallest tree. So to put it a little bit more specifically, here's the short version. The short version is just each key is spelled out along some path from the root, and common prefixes are collapsed as much as possible. Right? So this idea of collapsing common prefixes is what we really mean when we say that we want the smallest tree such that those things are true. We're not going to waste our time and space representing a common prefix between two of our keys more than once. Okay. And this kind of data structure, a trie, is helpful for implementing, it could be an associative data structure like a map where the keys are strings, or it doesn't have to be. It could just be a set, for example, where you're trying to put a set of strings together in a data structure so that later you can pose membership queries. Okay, so let's go ahead and think about the actual structure of a trie. Let's draw a trie for this data set. So here we just have a few keys which are all strings, instant, internal, and internet. Right away, you can see some shared prefixes, right? These strings are similar, they start with similar prefixes. And so we're going to have to apply this principle of collapsing the common prefixes when we go to make this trie data structure. And in this example, this is a associative data structure we would like to build, where with each of these keys there's going to be an associated value, and this table is showing you the key value mapping. Okay, so let's start with the root. Let's put the root up here at the top of the picture. So let me just draw a root here. Okay, and let me start by adding one of the three keys. I'll start with the first one, the key instant. Okay, so here I am at the root. I'm going to draw a child edge down to a new node, and that is going to be labeled I. So we're starting with, let me use red here. We're starting with I, the first character of the word instant. Okay, so there we go. Again, all the edges in the trie should be labeled with a single character from the alphabet, and a node can't have more than one child edge with the same label. Okay, so there's the I. Then I'm going to draw the N as the next edge label. Okay, and then for reasons you'll see in a moment, I'm going to sort of go off to the side with my next edge, and the next edge will be labeled with the next character in the word instant, which is the letter S. Okay, let's keep going. After S comes T, after T comes A, after A comes N, after N comes T. Okay, so there's the word instant, and in this trie data structure, we're going to take that associated value, which in this case is the number 1, and we're going to sort of put it in the node that comes at the end of the path. Right? So if that's the path labeled instant, then we want to put the value, right, the number 1, in the node that's at the end of that path, labeled instant. Okay, so there we go. We added instant to our trie. Let's move on to the next key here, which is internal. And, of course, as we've said, we don't want to represent common prefixes more than once. And instant and internal have a common prefix. It is the prefix in. Okay, so they both start with in. After that, they're different, right? Instant has an S next and internal has a T next. But that means that we're going to reuse this part of the trie. We're not going to make a new path labeled IN. We're going to reuse that path. And, therefore, when we go to add internal, we're just going to make a new child of that existing node, the one that's already after the IN. And this new child is going to have an edge labeled T, because that's the next character in internal. Okay? So int, and then we'll do E, R, N. Okay, and then for reasons, again, that we'll see in a moment, I'm going to draw the next edge sort of coming off to the side here. This is the word internal, so the next letter is A, and then the final letter is L, and then here's our final node, and again, I want to put the associated value, which in this case is the number 2, at the end of that path. Okay? All right, so now we've added 2 of our strings to the trie. We only represented their shared prefix of IN once in the trie. Great. So now let's add our third string. Our third string is internet. Internet has a shared prefix with internal. It's got a nice long shared prefix of INTERN. All the way up to there is a shared prefix between these second 2 keys. So again, We're not going to add a new path with this label. We're not going to make a copy of any part of this path. We're just going to reuse it. And internet we'll add by just branching off here. Internet, so E is next, and then T is there, and we're done, right? And then in this node, we'll store the associated value for internet, which is the number 3. Okay, there. So there you go. There was our trie, right? It obeys all these rules. Each edge is labeled with a character from the alphabet. We're just using, basically lowercase English letters as the alphabet here. For a given node, at most one child has the label C, right? We would have violated that requirement if we had added a redundant path, like once we'd added instant. If we went to add internal by making a new path over here and labeling that I, right, then that would have violated this second constraint that says for a given node, at most one child can be labeled with a character. And each key is spelled out along some path starting at the root. That's true. There's instant, there's internal, and there's internet. Okay. So there's our trie. There it is, printed a little bit more nicely. Okay. All right, so you get the idea. This is a tree-shaped data structure where the keys are spelled out along paths that go down from the root, and common prefixes are collapsed so that we only represent them once. We don't redundantly represent them more than once. Okay, so having built the trie, we ought to be able to query the trie. And since this data structure is, perhaps a set or perhaps an associative data structure, let's treat it as a set for the moment. The main query we'd like to be able to do is a membership query. Right? Given some query string, is that string one of the ones that we put into the trie? And so let's see how we might answer this question with the query string infer. Okay, well, we're going to go, there's going to be an algorithm here that we use to query the trie. And because this algorithm is going to have a core idea that we use again and again, I want to describe it clearly and give it a name, okay? So the process we're going to go through is one where we start at the root, and then we look for a path leading down from the root labeled with the successive characters of our query string, right? So in this case, we're looking for a path labeled INFER. And a process like this where we start at the root and we look for a path labeled with characters from our query. Again, because we're going to use this core idea so many times, I want to give it a name. I'm going to call it walking down. So we're going to walk down the trie according to the characters of infer and see what happens. Okay, so in this case, what happens? I start here and I'm going to walk down according to the characters of infer. Start with this I. So, oh, look, great. There's an outgoing edge labeled I. So the first thing I do is I follow that edge to the child. Now I look at the next character for my query, N, and now I'm here, right? And I ask, do I have an outgoing edge labeled N? And I do, great. So I follow that edge, I go to its child, and so now I've done I and N, and then I go to the next character, F, next character in my query, F, and oh, well, now I'm at this node, and there is no outgoing edge labeled F, so what happens, I'm going to call this, I fall off. There's no way for me to go forward. There's no edge for me to follow that actually has the matching character from my query. So that tells me that the query is not there, right? If the query were there, then there would be a path and I would never fall off, right? Every character would match and I wouldn't fall off. If I fall off, it means my query is not there. So in this case, we walk down from the root, but eventually we reach a character from our query for which there is no child edge labeled with that character, and we have to stop. Okay, and we can answer the question, no, right? The word infer is not one of the keys in our collection. Okay, let's try another query, a different query. This time we'll try the word interesting. Okay, and I go a bit quicker this time since now you sort of get the idea of what the walking down query is doing. So again, we start at the root, and we're going to follow characters labeled I, N, T, so far so good, E, R, E is my next character in my query, but there's no outgoing child edge labeled E, so what happens, I fall off, right? Oops, I fall off. And that tells me no, the key interesting is not present. Not present. It's not one of the keys I use to build my data structure. Okay, all right, so those were both two examples where we walked down and eventually we found a character in our query for which there was no outgoing child edge. Let's try another one. Let's try the query insta. Okay, so let's start at the root and we're going to follow INSTA. And we made it to here, right? And at no point did we fall off. Okay. Now, one of two things must be the case, right? If we manage to match all the characters from our query without falling off, then either our query is one of the strings in the collection, and the answer is yes, or our query is it's just a prefix of one of the strings in the collection, and the answer to the query is still no. Even though we didn't fall off, insta may not actually be one of the strings in the collection. In this case, it's not, right? Insta is not one of the strings in our collection. Instant is one of the strings in our collection, and insta is a prefix, but insta is not one of the strings in our collection. So how would we notice that? Well, in this example where we marked the leaves, it happened to be that all the leaves are at the ends of each of the strings in our collection, each of the keys in our collection. So we would just notice that the node that we ended our walk down at is not one of the ones that has an associated value. And that would tell us that it wasn't one of the ones in the collection. It was merely a prefix of one of the strings in the collection. Okay? No value associated with this node, so no, insta was not a key. If instead our query was the string instant, then as you can see, exactly the expected thing would happen. We would walk down, we would get to here, we would notice that that is a node that has an associated value, and that tells us for sure that the answer is yes. Instant is one of the strings in our collection. Okay, so that's the basic mechanics of how we query the trie data structure. Okay, great. Well, we have a few questions about this trie data structure now. We see how it works. We see that there's at least some cleverness to it in the sense that it's not wasting space representing common prefixes more than once. So let's ask some questions about how big it is and how fast these queries are. Okay. So first a question about how much work we're doing during that querying process, the walking down process. Okay, so say we are querying with some string which we'll denote with the variable capital P. So our query string is capital P, and the length of our query string is n. So if we're checking for the presence of that key in this trie, we have to traverse at most how many edges? Okay, well I have to take the characters of P and go match them to edges successively, character by character, and the only thing that might, quote unquote, go wrong would be I might fall off. And I could fall off at any point in that process, which is why this is an upper bound, right? We're asking what's the most number of edges I might have to traverse. Well, the most number of edges I might have to traverse is just equal to the length of the query string, right? That's the case where I never fall off, and therefore I do the maximum amount of work, which is I have to traverse an edge for each of the n characters of my query string P. All right, so what's the upper bound? It's n. I have to traverse at most n edges. Okay, now let's make a statement about the size of the trie. All right, so if the total length of all the keys that I added to the trie is capital N, right? In other words, if I took all the strings that got added to this trie data structure and I just took all their lengths and added all those lengths together, the total length of all the keys, if the total length of all the keys is capital N, then what is an upper bound on how many edges the trie must have? Okay, well, let's think about, since we're asking about an upper bound here, it might be helpful to think about, well, what's the worst case? Right? The worst case is that every character of every string, every key in my collection required the addition of a new edge, right? So in other words, the worst case is no prefix sharing. There's no common prefix between any pair of keys in my collection. That would be the worst case. That would be the worst in the sense that I would have to add the most total edges to my trie data structure. But we know very well what that worst case is. The worst case is each character of each key requires that I add exactly one edge. Right? So there can't be more edges in the trie than there are characters in all the input sequences. So the answer to this question is that the upper bound is capital N. Right? So if the total length of all the keys is capital N, then the total number of edges in the trie that I build from those keys can't exceed N. It could be smaller than N because there can be prefix sharing, like there is in this example that's on the screen. But it can't be any larger than capital N. Okay. Well, let's think a little bit more about how much work we're doing, because it's nice to know that if our query has length n, this is now back to little n, lowercase n, it's nice to know that if our query has length lowercase n, we don't have to traverse more than lowercase n edges. Wouldn't it be nice if we could think of the amount of work that we're doing for each of those edge traversals as constant? Wouldn't it be nice if we could think of each of those edge traversals as constant work? Well, whether or not it is constant work, whether or not it's reasonable to think of that as constant work, a single edge traversal, depends on what's the data structure we're using to represent the outgoing edges from a node. Right? Because to do this walk-down procedure, we have to repeatedly ask this question, is there an outgoing edge labeled C, whatever the character is? If so, I need to follow it, right? So there has to be both a way of knowing whether there is an edge labeled with character C, and then there has to be a way of looking up what is the node on the other end of that edge, right? So it has to. We need some associative data structure at each node that tells us what we can do as we walk down the tree, the trie. So one such data structure would be some sort of map data structure, right? So some concrete data structure that, as its abstract type, is a map from characters to nodes that would be the children. And so this might be a hash table. It might also be like a pair of parallel sorted lists, right? List of edge labels, list of nodes that have those edge labels in parallel. But at any rate, if we assume that it's something like a hash table, right, so then we know that these lookups are going to be efficient, right? With a hash table, we might say that constant expected time is what we could expect from that hash table so that we can ask the question, is there an outgoing edge, and retrieve the corresponding child node. We can assume that that's something like constant time. Reasonable to assume. And if we assume, therefore, that one step is constant time and we're doing at most n steps, then it is reasonable to think that we are doing a big O of n procedure when we are asking, is this query string one of the strings in the collection? And obviously, sort of same thing if what we're trying to do is not only figure out if this is one of the keys, but also retrieve the corresponding value. Because after all, our walk down from the root will end at exactly the point where the corresponding value is, so the only additional work there is to just return something that we've retrieved already from the bottom of the tree. Okay? Or from the end of our walk. It isn't necessarily at the bottom of the tree. So, for example, we could use this data structure instead of something like a sorted parallel arrays of keys over here and values over here. We could instead take all the keys in this picture, for example, and all the values in this picture, and put them all into a trie data structure, right? And I'm giving a sort of suggestive example because this index here is a k-mer index, could be a k-mer index of a string, where these are k-mers of length 2, right? K equals 2. Okay? So we could take all of these and put them in a trie, and I'll just show a piece of the trie. This isn't the whole trie, and as you can see, I'm sort of arranging it left to right on the slide. This is just a piece of it. But you can see what we've done, right? So starting at the root, I've now shown here, right? There's two possible keys spelled out here, CC and CT, right? Corresponding to this part of the table. Right, so CC and CT. CC actually occurs twice in our table, so it's associated with these two offsets, 12 and 2. So I'm saying associated with this leaf node is going to be like this list of offsets, 12 and 2. Likewise here, associated with that node is going to be offset 6. And if I were to fill in the rest of this trie, you can imagine I now have a complete associative data structure for this table. But before I fill it in, let's just, as a sort of challenge question, think about, well, how big is that trie going to be? And I'm going to suggest a sort of shortcut or a trick for thinking about how large the trie is going to be in this case, which is to think of it level-wise. So there's only one root. Okay, so that part's easy. But then here's one level down from the root, all right? We've already drawn one of the nodes at that level. But it's pretty easy to figure out how many nodes there are going to be at this first level down from the root. Because as we look at these keys, right, we see the keys start with A or C or G or T, right? So those are all possibilities for what will the first character be in the key. So we know that the first part of the trie, the first level, is going to have 4 nodes in it, right? We know at least that much. Okay, so now the next question, we're almost done. The next question is how many nodes are going to be at this level, right? 2 levels down from the root. Well, there are going to be as many nodes at that level as there are distinct keys of length 2 in our collection. And I've intentionally put same keys as separate entries in the index, so we have to sort of collapse them in order to get the answer to our question, right? So we have to ask how many distinct keys are there here? Well, 1, 2, 3, 4. This is the same as the previous, so I don't count that one. It's not a new distinct key. All right, so 4 so far. 5, 6, 7, 8. So there's going to be 8. So 1 at this level, 4 at this level, and then we just argued that there's 8 at this level. So the total number of nodes in the whole trie is going to be 13. All right, so there's the complete picture, inclusive of those 13 nodes. Now, before I end this video, I just want to say tries are not the only data structure that are useful for representing a collection or an associative data structure where the keys are strings. There are other possibilities. One such possibility, which I'm showing a figure of here, is called a ternary search tree. It's sort of a slight generalization of a binary search tree, but to account for the fact that the keys might be not scalars, but sequences. And so this is one possibility. But tries are the idea that we're going to stick with for a while here as we talk about suffix tries and then suffix trees.